So my last presentation for today, then you get rid of me, has a title, Cutting Tools and Cutter Head Design. I would like to give you a slightly different approach here, a little bit more, and want to give you an introduction into the main topics the cutter head has to fulfill, the main tasks, and then showing you some examples and the development of the cutter head design over the years. And then, and the last point, which is not the least, it is the most important for you as a user, is the cutter head maintenance and the cutting tool maintenance. I will start in the 70s and 80s. That was the Wild West for the tunnel boring machines. It was driven by personalities in production as well in construction. The TBMs were all new. Nobody had, let's say, any experience, so it was starting practically from scratch with sometimes interesting designs. And this is one example for a hard rock machine. And you could see a totally different approach at this time in the 80s. Nowadays, with practically becoming a complete industry, there's the stress and the request for component standardization, because it's now a full-fledged industry with variations, and so you have as well strong competitions between the different manufacturers. And so there is now the drive to have standard components, which you can nicely see as well, especially on the cutter head designs of this hard rock TBM, where you have a center which you can practically use for a range of diameters, and then you attach here to the sides different parts, which then adjust practically and bridge to the excavation diameter of this project. You have this with hard rock TBMs. Of course, you have this as well with soft ground TBMs. So that shows you how far we develop. We develop practically from these early single-on designs to the same system as the car industry does, with basic components which you can repeat throughout the range, and then with just attachments and adjustments for the single projects. Cutter head design. What are the tasks of the cutter head design? First and most important, it is your tool carrier, which carries all the and which practically guarantees that the tools are reaching to the tunnel face and acting on the tunnel face. It should be robust enough, the cutter head, that even with full loads and with eccentrical loads, your cutter head structure is not deflecting, so you keep always a specified contour cutting through the ground and rocks. As well, it's not a cutter head you cannot understand anymore as just a piece of dumb metal and as a hollow structure which carries you the material. It as well has carries a lot of sensors. It carries a lot of supply lines. I've shown you this before this morning with the EPB machines, for example, with foams, with water jets, and as well then with various sensors, just to say the wear sensors which you have as well. You equip then your tools with rotation sensors. So it's not just a steel structure. It is a carrier of a lot of supply lines and with a lot of own equipment. And then last but not least, you can build up the structure as well as a full-fledged compressed air chamber. So that is, on some projects, we have even that task. So it's a wide range for cutter heads. I just want to show you here in the very beginning, there where times were easy. You had here this about 4-meter machine with a very open design, with just a 5-star cutter head structure, a small axle in the middle behind with a drive behind. small gearboxes, and then you had here some scrapers, which you probably still can count with 2 hands, and very simplistic. And if you go and look now, we have sometimes cutter heads which are carrying more than 400 tools, and you have practically a huge task just to managing the tools and know where which tool is and in which stages it could be. So those are practically the opposite, what it comes from and where it ends up now. What is important for you? It is important for you that you have practically the correct setup for the tooling for your project. You have to select the right tools. If you have hard rock, you have or embedded boulders, you need cutting discs. If you have, and you for sure need anyway the scrapers which are behind. And there for you to let's say, to check or to see the quality of the design is then as well, especially when it comes to the discs, that you have the correct spacing size-wise, because they only have a limited area where they act. And if you have too wide spacing, then you have your tools in the middle which are not getting protected practically, and which will collide then directly with the remaining rock in the middle. So your disc spacing is something you can easily check by yourself with a centimeter, and you can actually there evaluate then a little bit about the quality of the cutter head. So I must say, of course, it depends as well a little bit on the quality on the rock. The more brittle the rock is, it's easier to split it up and have wider trenches. And the other way around, if you have a soft rock, it just makes a track. I can show you here. You can see nicely here the traces of the discs in a soft ground application with embedded boulders, which is quite typical for the Northern European part. Where you see how they drive the disc, make their pass just ahead of the scraper and then destroy the embedded boulders before the scrapers reach to that boulder. So they practically protect the rest of the structure. Here again, you can see that as well. The discs are protruding as well. Here, all the other tools, they are in the forefront and practically fighting through the hard part of the excavations. Same here from a new cutter head. You can see it here as well, very nice. That is the level of the scrapers, which are reaming off all the material, and the disc cutters are sizing it down, the rock material, to manageable parts, and they should always be higher, protruding out of the cutter head structure. Another thing what you can see here nicely as well is your base structure of your cutter head is protected with wear plates. Those are special wear plates out of a special hard metal, which have the only purpose to protect practically the other part, the softer structural steel. Here again, one of the examples for the supply lines from an EPB TBM with the different injection nozzles, evenly distributed all over the area all over the cutter head area. So just to give you an impression, and those lines have all to pass through a center. You have there a English expression now missing, a swivel where they practically a rotating joint where all the lines from the cutter head go through into the stationary part of the TBM. The cutter head can be attributed as well with some mechanical phase support. It is different between the different types of philosophies. Some countries are having a strong idea that they should use the the cutter heads as a emergency support system for the tunnel face to stabilize it in case you are missing the active face support, which we discussed before. And that is developed in different countries in different ways. And I just want to show you here now a structure of a cutter head, which you can see here for a hard rock application. It's an open gripper TBM. That one has no, let's say, mechanical face support capability. The discs are welded onto the basic structure. They are protruding freely into the space practically, and there's no, let's say, plates in between for any support. This cutter head is designed for a nice, hard, self-supporting rock where you actually just can speed through as fast as you get. And for that, for high-speed advance in hard rock conditions, that's the design for. Here it's totally different with the hard rock tunnel boring machines. Here you can see how flat the area is, the cutter head is designed. It has very flat space in between. The cutting discs are recessed. They are just poking out as much as necessary for doing the cutting. And then give as well a lot of, could give as well a lot of mechanical support to any blocky material to hold it off. That is especially important for if you have loose, if you're tunneling through loose material as well, where actually material could fall into your, from the tunnel face and could get caught by the rotating cutter head structure and thus blocking it. With that design, you try to minimize this danger and to have a better control, let's say, of the excavation you do actually. Penetration rates are here, as you can imagine, totally different than that from the TBM before. There it's just the typical excavations as you have. We have as well mechanical face support for soft ground TBMs. It's kind of a dying design, not that many anymore. Here's an example from, I don't know, somewhere in the 90s with a star plate here and then flexible support plates as well, mostly spring-loaded. We have here another example. It's a three-star cutter head structure, and as well here the plates inside to give mechanical support, so they are not working with either bentonite suspension or EPB foam. It's purely on mechanical support. Here's a closer picture of that. It has very strong limitations. It works in one type of geology, nicely not supporting, so it's and without any adhesion. As soon as you have any type of adhesion, that type of design ends up mostly in very low advance rates, as you can imagine, because practically there's no space for any material to pass through, and it must be raveling inside by itself. Those are pretty seldom, and actually I am not aware that they are still built. Normal mechanical face support systems, here again, just a couple of examples just for you to show in soft ground TBMs how different it was. Here, that was in the 80s, a design of an EPB TBM going through under the channel between Britain and France. One of the TBMs, that is a typical design there as a little bit later with smaller openings, huge mechanical face support. And here you have actually a more or less current design from another TBM, which has more or less nowadays typical opening ratios and stuff, so they are quite typical design nowadays. That was with the EPB TBMs. Here you see a couple of examples how it developed from the slurry TBMs. There it was actually more extreme, the influence by contractors and by nations. The European contractors were tunneling a lot in soft ground with embedded boulders. So what they always needed was good space for communication. The idea was to have a very good communication to the front, with your pressure, and then as well to have space to actually get the material in, and then to have here a stone crusher for getting the boulders into the stone crusher and then get it pumped out. That were TBMs, as you can see, without disc cutters. So they were actually working here even with cobbles and boulders without any disc cutters. The spokes at that time, the bearings were not designed for that. So even here, that is from, so those are pictures from German contractor. This TBM was in Lyon by a German contractor, was going under the River Rhône and Saône. And it actually, even there was gravel, like from a mountain river, without any fines. And you can see even there they maintained large openings, no disc, no nothing, because at that time it was just not there, the technology. Still, all machines made it, and at that time it was a way, but let's put it this way, the interventions into the front of the TBM were a frequent sport at this time, more usual than today. In Italy, same type of TBM use, very open spike. You have to see that is 10 meter something TBM and practically only 6 spokes. And so when you enter here during the operation for maintenance, you are standing practically right in front of a complete wall, just standing there in front of you. It's quite impressive. And then you had the French design. The French design, they always loved closed cutter heads. At the end, I don't know why, but that was practically where they came from. They had always the favor for closed design. Probably Karin knows that better than I do. So that is the Metro Paris TBM, slurry TBM, and with a totally different cutter head design, and more or less used at the same time, the TBMs. And then there was an even extension that was at that time one of the largest TBM, and you can see it's flat, completely flat, no just these little slits for letting the material pass through. Was designed for very soft ground, but obviously they wanted to have mechanical phase support as an additional safety to their usual active phase support system by bentonite slurry. Nowadays, you will have problems defining or figuring out just by looking at the TBMs from the front. At least I cannot do it anymore. The TBMs look more or less quite the same, the cutter heads. They are carrying, or they have at least the capability to carry disc cutters. They have more or less the same structures. And so you really have always then to look in the back behind if it has a screw or if it has a pumping system to define it's a slurry TBM or not. So what do we have as well? The task is the communication and material flow. That is a very important task for the user of such a TBM, because at the end, the material has to flow, the excavated material has to flow through the cutter head structure, and at the same time, there must be enough space in the openings that you have actually back the pressure communication into the tool gap, so you know what the pressure is inside. So if it is blocked, then you can build up a high pressure here in the back, but you don't know what is there in the tool gap, and that's where you want to support the tunnel phase. So you need good communication ways, good pathways for the purpose of having your material flow as easy as possible, and the other thing is for having the pressure communication to the front. That is, has a lot to do then with the opening ratio of a cutter head, which is defining practically the relation between the total face area to the open face areas. And that is now typically around 35 to 45%. And so that is practically the way the cutter heads are working. In these channels, in these openings, you have to guide the material through as fast as possible. These openings have to be designed that they cannot or prevent to stick to the sides. So you do not build up any blockages in those openings. On some cutter heads, you end up with a deeper structure. And you can imagine there it becomes more critical, because when you pass through here, it's not always as nice as this little sketch here. If you pass through smaller holes and if they are deeper, it is of course more difficult to get the material through without having it sticking to the side, building up and on the side walls, and then reducing the transport capacity. That is something we come later. Here's a little research we did one time for a project to evaluate the cutter head openings, because it's not only about the actual size, it's as well about the distribution along the radius. We have practically this is cutting the diameter of the cutter head into 20 centimeters layers, and then just observing, okay, that is the increase in my tunnel face, in my face area with the increasing diameter. And that here is then the assumption of the open spaces in each of that radius. So what you can see is then that the cutter head had very small openings, or nearly no openings in the center part, which is it's one of the most difficult parts in the cutter head structure. But it had it here, and it was very difficult then for the material. Every material you excavate in this section has to pass then through somewhere different. And so you have through the openings, you have what we call a normalized material flow, where you have the opening. It's very easy to flow through. It's very small, the flow, material flow, but where you have here these reduced openings in the center part, then your material flow needs to be squeezed somewhere different through. And so you have here then the opening ratio, and you see that in the center it's not there nearly, but then you have here these typical ones. So, and there was then a little problem with additional wear, because what your material, which you excavate here in the center, what it has to do, it has practically to move to the side, to the next one, to the next opening. So this opening has additional traffic passing through. And that is here then the measurement of the wear on the cutter head structure, and you can see that it actually matches practically where the material accumulates. You had then here additional wear or severe wear on the cutter head structure. So it's not important that the number and the opening ratio itself. It's as well interesting to see where the openings are. And then last but not least, there's then the facility of having in large TBMs especially, you have then the possibility as well to enter into the excavation into the cutter head as you would enter into the excavation chamber. So you can actually use a compressed airlock. You can operate this at different pressures and have this way the possibility to go into the cutter head and exchange discs in a more controlled environment than doing it outside. This is especially done with these so-called XXL TBMs, the large TBMs. When they are in shallow alignment paths, they just don't have the possibility to do the compressed air intervention, standard intervention from the outside. So they then take the option as well for going doing the exchange from the inside. This is a picture here of one technician, and you see here that he is there with a let's say with a device, a retracting device to move back practically the discs or whichever tool is behind and to replace it from inside the spoke. It's not, well, it's only on special occasions. It takes tremendously long to make a tool change in these kind of conditions. And the other thing is it takes a long, there are not many tools which you can actually access through that. So here's an example of such a cutter head, and the disadvantage which comes as well, and which I would like to show you here. Of course, such a hollow structure then takes a lot of height because you want to enter into it and want to walk through it and work inside. So all your material flow has to go through this deep structure, and then you have these kind of deep holes where all the material is moving through. And you can imagine if I have a little bit of clay and it's nice and warm in there, then I like to stick to the sides. And then you build up easily here a reduction of your open face. Here's when this cutter head is lifted into position, you see here from the back, the center, and you enter practically through the center, and then you can go here into the cutter head spokes and do the changes from inside. But you can do it only on 3 o'clock and then 9 o'clock, because the others are a little bit too steep to go up or down. So those are the cutting. Now coming to the cutting tools, there are practically 2 different types of cutting tools on the market, or those are the choice. The one are the scrapers, as I explained before. These scrapers you receive in various, numerous variations, and from very simple ones to a little bit more sophisticated. You can have them with hard metal inserts, with wear plates on top. You can have them with fixed, with fast change lock devices or with bolt systems. So from many manufacturers you can get a lot of different tools, and it's practically, yeah. If you have a tunnel project, your TBM manufacturer will propose to you something, and then you have the choice, right? Same with rippers. Rippers is kind of the same. It's a scratching tool. It is used as a replacement for disc cutters in softer ground, and where disc tools would be actually not necessary. And you can use then the spots with ripper tools, which are pre-cutting and practically the tunnel face as well. As they are protruding quite far into the tunnel face, it is possible for you to have high advance rates as well with these type of tools. Scrapers are, as you can, those were then, as you can imagine, they wear easily off. So you have as well then split tools which have a wear head and a base structure which holds this. And as well, the same thing enormous variety all over the market for those. Here you can see a Japanese design for this. They have here used the space for the disc cutters with a double knife, and which is more or less the same, like acting the same like a ripper tool. They are just as well cutting right through, ripping through the tunnel face. That is the task. So here you can see that all the discs have been replaced by these type of tools. As well, it's the same. This is the accessible cutter head. And here you can see that practically out of all the number of tools, you only have these here in these big spots, which are actually then retractable from the rear. So all the other tools, you still have to go to the front. So then you know that you have some limitations in what you can do with these cutter heads. Disc cutters are acting different. They are not ripping through. They are rolling on top of the tunnel face. In rock, they are just pressed with high force onto the surface of the rock. They are overstressing practically the tensile strength, and then the rock below explodes. And the scrapers are doing then the work and moving the chips away. The discs are built more or less as well, depending on the design, in a way that you have here the cutting ring itself. It's either as a separate to the hub, or it is as a monoblock going just as one piece. You have here the axle where it turns, which allows it to turn, and then you have the bearings here for taking the load from the discs. Here as well, you have for soft ground applications, you could as well have the double discs, which are on one housing, practically two of these discs. And here's just another example of different, that is in the center part again, where the discs are designed in a special way, so to make it possible to have it installed in this very limited space here in the center. Here is just to show you how that works, how it is built up in reality. I took the chance, and this is again normally your sharp outer rim with a cutting disc on a monoblock system. You have then here the axle, which let it turn, and then you have the bearings, which allows the disc to turn. That is what it looks in a better state. You see here on a pure hard rock application, the cutter head, the disc cutters, as well protected with impact barriers, which prevent that the disc get a punch from hard rock in the lower part. They are designed the way that it should only happen here in the tips of the disc cutters. And so they have here this additional protection. That is what it looks a little while later, and you see they are heavily worn. The plates as well as the wear plates are heavily stressed, but the discs are more or less functional, as you can as well do service to them in the meantime, which you cannot do to those. Maintenance, that brings me to the maintenance. You have to see that the ripper or disc cutters are on the most forward position. The scrapers and bucket lips are the second in the row to work with the ground, and then you have the wear protection plates, which are positioned here on the surface to the base structure, and those are your defense lines against excessive wear. If you do not maintain those parts, especially the first two, which you can easily maintain, you start wearing off the fixed plates, which are very difficult to change. And once those are gone, then it gets to the base structure, and that goes then, compared to the wear protection plates, very fast and quite easy. And you lose then the capabilities of your cutter head, and the tunneling process will soon end. So what I would like to emphasize is, from the practical side, it is very important that you get a feeling for the amount of wear your cutter head is receiving when you start with a tunnel boring machine. And you can only do that with doing, in the beginning, frequent inspections, and just to get the feeling how much wear I receive with my tools. And then you start, let's say, adjusting your intervention plan to whatever comes out when you see, okay, I have more time and it's not as bad as I thought. And then you can, let's say, stretch a little bit your inspection frequency. Here's an example what happened when you missed to do the tool changes and the tool maintenance. You can see here that was a disc cutter at one time, and how deep that was. One level was going from here to there, and those go quickly. Those go quickly. That happens in a couple of meters. You can destroy a cutter head. That is another one which came actually by a surprise. That is in the slurry TBM. They can have as well these high wear problems. And you can see here, that is the surface. You see here the disc. They are lacking a little bit of maintenance as well. They are not operational anymore. They have flat spots, so they are not of no use. And the spoke was going all the way through on this level and was bridging that. And that was gone. And it was just by accident when the TBM came out into the reception shaft that it was realized that actually it was in such a bad state. There were only 20 centimeters left of the structure to hold the cutter head rim. Otherwise, it would have been falling down. And it was kind of a surprise. So again, cutter head maintenance or tool maintenance is the key. By now, there are as well not only manual tools, you have as well electronic tools which help you in the maintenance plan. It gives you as well, when you type into these systems, you can give, let's say, a report, or you can type into that when you did changes. And with this information, the systems can then estimate in which status your tools are and give you an indication. And that way you then have quite a good idea or what your cutter head status is and where you should look next time when you are there. The same as then with the graphical displays. You can have here information with the generations. And as well with with the systems, you can as well put the wear data as well in relation to the geology you are excavating through, and as well to TBM data. So with that, I would like to thank you again, and that's it. Thank you.